Welcome to this journey from NumPy to TensorFlow and keras. While we previously built networks from scratch, now we will master the tools used for production ready AI. TensorFlow acts as a bridge from research to the real world deployment on billions of devices. So, first, let's see what we will learn. We will learn all these things, fundamentals and then Einstein summation, everything that we have learned manually we will learn here now using TensorFlow. So first we will do the setup cell. I'll just run it. Uh, we are importing the TensorFlow and the new keras 3, which is a standalone multi backend import. We also check GPU availability and enable memory growth to ensure framework doesn't hog all your hardware resources. So finally, we seed both for NumPy and TensorFlow to ensure the reproducibility. Once this installation is done, we will move towards the building block of deep learning. That is a tensor. So we define our core data structure tensor here in the upcoming cell. These are multi-dimensional arrays ranging from zero dimensional to scalars to three dimensional tensors and three plus dimensional tensors, but with the superpowers like GPU acceleration and atomic differentiation. So let's see. Here we are defining one tensor from Python list. Here we are defining a Python tensor from NumPy array, and then here we are defining some special tensors, zeros, ones. We already know what are this, so let's just run it. Now moving forward, here we are defining tensor data types. We have already seen in our earlier collab recordings what are these data types and how they are used. I'll just move forward. Device management we can do. We can print the type of device. We can see the type of CPU tensor we are using, the GPU tensor you are using. Everything we can get the details using the dot device. Now next thing is a tensor operations. So we can do the element wise operation similarly the way we used to do it in earlier in PyTorch and NumPy. Similarly, square root, exponential functions, the matrix multiplication function, everything we can do here, the transpose and the inverse, reduction operation, all these things that we have already seen earlier. The same things can be done with TensorFlow, but with more GPU acceleration and atomic differentiation. So this is how it works. We can also do the reshaping and the broadcasting thing that we have seen. So you can see here we are reshaping this extensor. We have defined extensor somewhere. Yeah, here we have defined a extensor, and then we are reshaping it. We are also reshaping it, and then we are defined one more y tensor, and then we are expanding the dimensions of the tensor. We are adding some new axes. We are expanding the shape wise, and then we are squeezing also the tensors, and also we are broadcasting here. So let's see the output. All these functions we have seen in detail in earlier collab videos, so we are just going through the overview so that we can revise and then we can work on the main advanced part of the TensorFlow. Defining variables, all these things, we can define uh, variables here. So this is a critical concept, variable versus constant. Tf dot constants is immutable, but if we do tf dot variable, it is mutable and is used for trainable weights. This distinction is vital because gradient tape automatically watches the variables to compute the gradients, but it does not watch consonants unless explicitly told so. So that's why defining variables is important, and the consonant are immutable and variables are mutable. So we define variable like this. Let me just run it. So here we are trying to alter the variables and see how it is behaving. Next is the Einstein summation. Now we move to the einsum, the Swiss Army knife we have already discussed in PyTorch. Similarly, it's used here using simple string notation where repeated letters are summed over. We can express transpose, sum, and diagonals in highly optimized way here using in sum. So it's the same. We have defined three constant. Basically, we are doing in sum. Here we are doing the transpose. Here we are doing the sum of all elements. Here we are doing the sum of rows, and then same we are printing the diagonals, we are tracing the diagonals. So there are different kind of operations that we can do with in sum. Next is in sum product and the multiplication. So uh, this cell shows in sum handles the products, and from basic dot products to the classic matrix multiplication. We see batch operations. This is how we handle the complex math of transformers, where we use bqd bkd goes to bqk to calculate the attention scores between queries and keys in parallel. So this is how we use and sign sum for product and multiplication. All this detail, how does it actually work, what is the logic behind, we have already seen in the PyTorch video, so I'm just skipping it. The batch operation, as we discussed this one, uh, this is also handled very efficiently in TensorFlow. Uh, this this helps to calculate attention score between the queries and the keys in parallel. We'll see how we use it. I'll just run. So batch multiplication, attention scores, all this we can calculate using INSUM. This is all just using TensorFlow it's showing, but the main background, the logic behind it, we have already seen in the PyTorch video. This INSUM cheat sheet also we have seen earlier. I'll just simply run it. This cheat sheet we have seen earlier. Moving towards the part 3, that is the gradient tape automatic differential. So gradient tape is the magic that eliminates manual back propagation by performing operations inside with a tf dot gradient tape context. TensorFlow records the tape of your forward pass, and then visualizes the computation graph. So we can, let's see, we'll go through the code so it will be easy. So here we are defining a variable, we are printing the variable, and then we will record operation with the gradient tape, and then we will compute the gradient. So let me just run it. So here is our element, here we are performing the operation and we are computed the gradient, also we have printed the manual gradient also, and both are same. So this is how it works. We'll see the graph visualization of the computation. So suppose we have built a computation graph in the gradient tape, and then we are computing both a and b at once, and then let's see the computation graph here. So basically this is the function that we are doing. So graph will look like a into b goes to plus d, and then goes to the power and adds to e. So this is how it works. This is the gradient. And next we will see is we'll scale this up to compute gradients for entire vectors and matrices. So this is the example for matrix where we have weight w and x, and we are defining the gradient tape as the forward. Then we are calculating the loss also, and then we are performing the gradient. We are calling the tape dot gradient. So if I run it, we can see how vectors and matrices work with gradients, and this is our output where we have printed the wx and everything. Now let's move toward one of the important thing, that is um persistent tape. So this cell covers the advanced patterns like persistent tapes for multiple gradient calls and higher order gradients for second derivatives. So let's see how does it works for the second derivatives. So here we are defining our gradient tape, explicitly telling tape to watch this content, this constant, and we will do the gradient. So once this is done, we will update the constant, we will see like the tape is deleted. By default the tape is deleted after the gradient call is done. So we use persistent equals to 2 to call the gradient multiple times, so that it's persistent, and then we will call it and we will print the results, and then we will clean up the persistent tape by deleting tape. This is important part. And once that is done, we will see the higher order gradients. So we can loop it as tape 2 and tape 1, and then we can do two order gradients. And let's see the output for this. So first is watching constants and then using persistent tapes, and then we can see higher order gradients output also, that we have performed the first order derivative and the second order derivative. So moving forward to the TF functions and graphs, uh, we use TF function decorator to compile Python code into a fast and static C++ graph for massive speedups. And just let's see. So this basically we are doing without TF function with the eager execution, and this is how we implement it with the TF function with compiled C++ graph. Let's print the result of both eager and the graph and see which works. So both gives us the same result, but the function is fast. The function TF function compiles your data fast as compared to the manual process. So we use it for training loops and inference for massive speed ups. Now we will go to visualizing gradients. So this cell puts this all into a practice by visualizing the gradient descent in action to find a minimum function. So let's see, just run it. So basically we are now combining everything. We are plotting a gradient descent function. We are storing the history so that we can plot the graph, and then we will record the history. We will compute the gradient, and then we will do gradient descent step, and then we will print the final details, and then we will visualize the result to see how it actually works. So we can see final starting x, final x, and then final of fx, and we can see the loss function and then gradient descent path also here, where this is the minimum descent path. So this is how we use it. Now the next is neural network from scratch. So now we rebuild a neural network using only a TensorFlow primitive, no keras layer added. We manually define activation functions like ReLU and softmax, and then we will define loss functions like categorical loss entropy, and then the neural network primitives classes to manage the weights and the biases as TF variable objects, and then we will use the gradient tape for automatic updates. So let's see one by one how we do it. So the first thing we do is we will define the activation functions, the sigmoid, 10h, ReLU, leaky ReLU, softmax. How this function works in detail we have discussed already in the NumPy and PyTorch videos, so you can refer from there. So we have defined our activation functions here. Here we have defined our loss functions. Again, these loss functions, binary entropy, cross entropy, MSE, all these loss functions we have discussed in NumPy and PyTorch video. So the next is neural network from scratch. So we will create a neural network class where we will define the init, where we will define the layer and the activation name. We will define the self activation function. We will define the weights and the biases and initialize it, and then we will initialize the loop where we will do the initialization. uh, After the initialization we are setting up the biases, and then we are appending it, and we are storing the data in the history so that we can use it later for the plotting purpose. We will do first the forward pass where for each layer we will do the linear transformation. So here we are doing the linear transformation, and then activation function we are passing it, and then we are checking the output layer. For no activation function for now, we will just check the output layer, and then we will print it. Next is define trainable variables. We have defined returning the trainable parameters, and these functions basically convert to tensors if needed and select the lost functions according to requirement. Now for each epoch we are doing the forward pass with gradient tip, and we will apply the sigmoid for binary classification, and else we will apply softmax for categorical classification. We will compute the loss and then we will store the history. We will do the backward pass automatically, and then we are doing the gradient descent update. Once this is done, we will compute the accuracy and we will store it in the history. We'll print the progress and then we will return the history. So this is the predict function. This is the summary function which we'll use to print the summary. So this is how the neural network primitive class is created. Now we will test the XOR problem for this neural network. We have already seen this XOR problem, and so I'll just quickly run it and we can see if the output is correct, then we are okay with it. So see, we have this parameters trained and then we are training it. Epochs are running and we can see the predictions. The prediction is approximately in points and we are rounding it up, and then we are plotting the graph, which is exactly what we are expecting. So this is how it works. TensorFlow works with the neural network. Now we now transition to a high level keras API. Keras 3 is an elegant abstraction. Is an elegant abstraction that handles the weight initialization and device management for us. We will see how it explains the dense layers, and which is a simply formal implementation of activate y is equals to activation function. We'll see how these things are implemented and how we can use keras. So the main feature is it is multi backend, it has cleaner API and the better performance. So let's see first the dense layer explained. So we will see layer dot dense is fully connected layer, and how does it works here. We are doing this for the easy way, and once the sequential is done, we will move forward to the next is, that is functional API for more flexibility. So the functional API allows for complex graphs like ResNet, StyleScape, connection. We'll see in upcoming cells that how does it works. So the functional API allows multiple input output shared layers and then non-linear topology. Uh, First we will define the input, we will build a graph with then layer dot dense, then we will create a model from inputs and the outputs, and we will print the summary. Let's see, we will pass an input and let's see how it actually works. So this is the model created for the functional API. We have input, we have two hidden layer and one output layer, and this is how it actually works. Now next is the subclassing. So subclassing is basically it provides maximum control, allowing you to define custom logic in call method. So we can add some custom logic while call method. So if you see, I'll just quickly run it. So when you call it, you can pass the hidden units and then activation function, and here we are defining an additional call function. Uh, During the forward pass of training argument control dropouts behavior, we can mention this is that dropout uh, argument which is defined during the training and can be used, uh, can be passed to do the maximum control, and then we will create a model and we will call it with sample input. I'll just run it, and you can see we have created a model with dense layers, and then the dropout also we have defined here. Total parameters, we can see trainable parameters, everything is defined here. So we have seen the three ways to build keras model: sequential, functional and subclass. Now in this cell we will compile the model by choosing the optimizer like Adams and loss function like binary cross entropy. So let's see compiling and training. We have created a model, we are compiling using Adams optimizer and binary cross entropy. So I'll just quickly run it and we can see the model is compiled with all these optimizer and loss functions. So the next is the dynamic builder. So this cell provides a dynamic builder function that lets us experiment with different architecture dropout rates and batch normalizations with just a few arguments. So let's see, I'll just run it quickly. So we have this create MLP where we are defining it. This will create a multi-layer perceptron with given architecture. This architecture model, sequential model, then input layers, we are adding hidden layers, and then we are adding the output layer, and then we are returning the model. So we can create with different architecture. We can create a small net, we can create a medium net, we can create a deep net based on the arguments that we are passing. I'll just run it. So we can see we have a model, sequential model, and we have created this sequential net model with deep net with dropout and batch norm. So this is how we define it. The next part is complete training. We conclude the real world demos. So we will again see that XOR example using keras, and for cleaner code, let's see this. I'll just quickly run it. We already know the purpose of this code, so what this basically do and how we are using it. So basically see what we are doing. We have defined the x and y data. We have defined random seed, and then we have defined a model that is a sequential model. We have given the activation functions. Then we have defined like compilation. We are compiling the model by optimizer. We have provided the Adams optimizer and binary cross entropy. We are training the model to XOR and YOR with 500 epochs, and then we are printing the results. So we can see we have this training and then prediction, and then this is the epoch loss graph. So the next is the moon classification, the same thing that we have done in PyTorch. The same thing we are doing here. The only difference is now we are using keras. We are generating moon data sets, and then we are taking the data, we are splitting and shuffling the data, and then we will provide that data to the model. We will compile it using Adams optimizer and binary cross entropy. Then we will train the model, and then we will print it. So this is how the moon classification works. We are training it again. I am running the code. Meanwhile it's training, we'll see we'll visualize the decision boundary. So we can't do it before it, so let it run completely and then we will visualize the boundary. So yeah, this is completed. So training is done. Final accuracy, we can see epochs are decreasing. With increasing epochs the loss is decreasing steeply, and the accuracy is also increasing. So we will also visualize the decision boundary for it. So you can see decision boundary is very pretty clear. So and very fast, the performance is very fast. The next is the digit recognition, the same problem that we have seen earlier. So we will load the data set, we will normalize it, we will split it into test and train data. Then we will do a model for multi-class classification. We will compile it with Adams optimizer, and for loss we are doing is sparse categorical cross entropy for integer labels, and then we are training the callbacks. We are doing the train, we are fitting the model, and then we are evaluating our loss and accuracy, and then we are plotting the graph accordingly. So I'll just run it. Once this is done, we will visualize the predictions and then we will be done. So this is done. We will visualize it quickly. We can see the predictions, everything is green. So the last thing is callbacks to the powerful control. So our final demo we have already done. Now we introduce callbacks, the powerful tool for like early stopping and reduce LR on plateau that monitor training and take actions if model stops improving. So this is how we define callbacks. We'll define the callbacks and we will give early stopping monitor, and then we will reduce the learning rate when stuck. And this is how it helps, like in early stopping, model checkpoint, reducing tensor board, and then learning rate scheduler. All this thing it helps. So this is the summary that we have gone through. Uh, what things we can do with numpy, what thing we can give with tensorflow, and what things we can do with keras. All these things we have gone through, and then we have done also the keras and pytorch comparison. And the best practices that we have seen is data processing, and then model design, training, and then debugging, and then we do the deployment. So this is the cheat sheet that we have already discussed, the important uh, mm, syntax and functions that will be useful for you. So that's all for today. Thank you so much.